Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on particle swarm optimization. In the past tutorial, we talked about how to perform a bounded particle swarm optimization, and in order to do that, we define a particle space or domain space or particle domain. So particle space is basically formed by all the intervals that we give to the PSO as the initial intervals for particles, and then it just has one method is particle inside, and it checks the position of the particle with respect to the search space, the initial search space. Okay, so the coordinate I of the position of particle should be inside the ith interval. Okay, and then we said that if we don't do this check, then we always get an unbounded optimization. So the particles can in fact walk out of the initial search space, initial position space, but sometimes we want particles to always remain in the initial search space. Okay, and we defined this class to check for that. And then we said that one approach is to, whenever the particle goes outside, what we do, we move it back. Okay, and if the particle is outside, we don't update the velocity either. So we update the velocity, we move the particle, and then check whether or not the particle is outside the search space. If it is, we move it back and then revert the velocity to its previous value. Okay, now let's look at another example of how useful PSO can be. Now, so far we have PSO, unbounded optimization and bounded optimization. Okay, let's assume we have this type of problem. Okay, so we can use PSO to find a desired solution for a constrained inequality, for a set of constrained inequalities. What do I mean by that? So let's say we have a set of inequalities. Let's say M inequalities. F0 is a n-dimensional function of x0, x1 all the way to xn minus 1, and it's supposed to be between c0 and d0, f1 between c1 and d1 all the way to fm minus 1 between c m minus 1 and dm minus 1. So we have m inequalities, m inequalities. Okay, m. And then besides all the inequalities, then the variables x0, x1 all the way to xn minus 1 are also bounded. So we have some constraints on the variables as well. So x0 between a0, b0, x1 between a1, b1, and xn minus 1 between an minus 1 and bn minus 1. Now we can use PSO. Now in most cases, when we try to numerically solve such problem, we're just looking for one possible solution, right? We don't necessarily want all the solutions. So what we can do, we can actually use PSO, a bounded PSO, to find a solution to this problem. And the way we do it is that, okay, so we define an n-dimensional particle space because we have n variables, and then a0, b0, a1, b1 all the way to an minus 1, bn minus 1 are basically the bounds of the PSO, which we already know how to implement. So that's not a problem. The problem is that how do we convert these m inequalities into basically a fitness function, because remember PSO only took one fitness function, one n-dimensional fitness function. And now what we can do is that we can in fact define a simple fitness function that is minimized or maximized, one of these two, either minimize or maximize, when all these conditions on the f functions, f0, f1, fm minus 1 are satisfied simultaneously. Okay, so set the bounded optimization flag to true in the PSO for these inequalities, and for these we define a fitness function This is our fitness function, and the fitness function is basically we define it in such a way that if all the conditions or the inequalities on f of I, f0, f1, fn minus 1 are satisfied, this fitness function returns +1, for example. And if at least one of these inequalities is not satisfied, we return -1. Okay. Now what happens here is that if we are looking for the solution using PSO, we have to look for a solution that maximizes this fitness function, because then maximization only happens when we basically have all these inequalities satisfied. So all the variables are within the bounds and all the inequalities are satisfied, so we have to maximize this. Now of course we can define this fitness function such that it returns -1 when all these inequalities are satisfied and +1 in the other cases, and then we have to minimize it. So this is one way that we can basically convert this problem into a PSO optimization problem. And again, PSO is very simple and pretty fast, impressively fast, because it's just a bunch of summations and multiplications, nothing more. So PSO is very efficient, and we can use such method to solve this type of inequalities. Now here's one example that I have. In this example, basically I have two inequalities, f1 which is x squared plus y squared. It's a circle centered at 0, 0, and I want it to be less than or equal to 1. Okay, and then f2 is x plus y, and I want it to be between 0 and 1. So I have two inequalities, two-dimensional space, and one is inside the unit circle, and one is between two lines, y is greater than -x and y is less than -x plus 1. All right. So variables domains, which are basically my PSO bounds, are I want x between -2 to 2 and y between 0, 5. These are my variable bounds. Okay. So I want to solve these inequalities, find just at least one solution that satisfies these two inequalities and these two bounds. So I define a fitness function, let's say f -1, if f1 is true and f2 is true. Okay, and then +1 in other cases, and then the PSO problem is to try to minimize this function. Okay, because if this function is minimized if and only if that f1 and f2 are simultaneously true. Okay, now here's an example. I have a video here. I've already written the code and executed it, and here I'm plotting this blue circle is basically the first condition. First of all, the x and y are the particles at x is from -2 to 2, and all the particles always remain in this space, and then y is from 0 to 5. Here I'm plotting from -5 to 5, so let's make it -5 to 5. All right, so x from -2 to 2 and y from -5 to 5. This blue circle is the first inequality. These two lines, the red and the green, are the second inequalities. All right, so this red line is y equals -x, and this green line is y equals -x plus 1. Okay, now what we do, we define this fitness function and then pass it to PSO and run a minimization. And here I'm tracking the position of all these particles. I believe I'm using 20 particles and 50 iterations. And let's look at what happens to the particles as the PSO evolves. So iteration 0, iteration 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. You get the picture. So all particles try to stay basically in the blue curve and between these two lines to satisfy this objective for the fitness function. Let me just play the video quickly, and you see what happens. The particles eventually come in the gather in the blue circle and between the two lines. And that's how we can solve this inequality. And obviously we have infinite number of solutions, but in reality we're just looking for one possible solution. All right, let me just also go for a screen and play this. And again, as you can see, we are getting so the particles are basically converging here, and that gives us a good solution, a viable solution. All right. Okay, let's head to Eclipse and try to look at the code that I wrote for this. So in our demo PSO project, I put a test inequality here, a new class, and here in the main function, what I'm doing is I'm creating my fitness function. All right. So fitness function, remember t is the n dimensional. So t is n dimensional. Here n is equal to 2, t is 2-dimensional, t is an array. So I define x as t0, the first component, and y as t1, and then define f1 x squared plus y squared and f2 x plus y, and then say okay, if all of my inequalities are simultaneously satisfied, which means f1 is less than 1 and f2 is greater than 0 and f2 is less than 1, return -1, else return +1. all right, so this is my fitness function, and it's going to be minimized if and only if all my conditions, inequalities, are satisfied. And then I define a PSO object, new PSO, and if you look at the declaration, the first argument is, the first parameter is the number of particles, which is 20, and then my fitness function, and then an array of intervals. Okay, and I want my first variable, which is x, to be inside -2 to 2 and y to be from -5 to 5. And again, I want to get to these conditions, so I want to minimize the PSO. The PSO procedure is minimization, and this is the key. I want to ensure that my variables x and y, or the position of the particles, always remain within these bounds. So I set the set bounded optimization flag to true, and then I set the number of iterations to 50. Okay, and then I run the PSO. So here I'm using this method called next in PSO. If you recall, we had this solve method. For the number of iterations, we update the particle best params, update best params, which is the swarm's behavior, and then move particles, and then go to the next iteration. Now the method next is basically only one step each time, so it just updates and moves, and that's it. And then I can call next many times to evolve the swarm as many times as I want. So this next method just one step of evolving the swarm. Okay, and it's useful when I want to look at the position of particles at each step. All right, so here I'm also plotting the circle. So t in a parametric way, so t is the parameter of the circle from 0 to 2 pi, and then x of the circle is cosine, y of the circle is sine, and then I plot the xy, and then I'm plotting y equals -x, and then I am plotting y equals -x plus 1. These are the two bounds of this inequality. All right, and then at each step of the PSO, I'm getting the list of particles and getting the xy arrays as the first coordinate of the position of each particle and the second coordinate of the position of each particle. right? Remember, the get position method returns a vector nd. In this case, it's two-dimensional, and we wrote this at method at some index that returns the component of the vector. And then render the plot, render the figure, and then plot x val, y vals, which are the particles, and then no line width, just the markers. So particles are just represented by markers. And set the xy limits of the figure to -2 to 2 and -5 to 5. Set the font to 13. And here I'm going to just show it. So render the figure and show it. So I can do this for each step. But in the for loop, I can also say maybe just a few selected steps. For example, I0 and the first step and the last step. Plot it. And this next step on the PSO is inside the for loop, so we in fact evolve the PSO as many times as indicated in the for loop. Here it's 50. All right, and then I print the best value and best position. So the best position gives the possible solution for all the inequalities, okay, and the best value, because we're minimizing, obviously we expect to see a -1. So let's run this. And it's a little bit slow, but okay, so we get -1, and this is the 0th iteration, the original particles, and then here's the result. You see almost all the particles are inside, and this is the majority of particles are inside the circle and between the two lines. That's how we solve it. And if you look at the result, 0.929 and -0.275, the sum of the two should be between 0 and 1, which is, and also the x squared, the square of 1 plus the square of the second should be less than 1. So this gives us 0.81, and this 0.09 yeah, so the squares are less than 1. All right, and we can even do, let's say we can also use less particles, let's say only one particle, and let's see what happens. So again, the first iteration and the last iteration. Here unfortunately we're not getting a correct result. The particles are way off. So I guess 2 or 20 particles is good. I guess with 10 particles we have to iterate for more than 50 steps. Let's go back here, run it. So 10 particles, 250 steps. We get a good result. Most of the particles are inside the circle. Let's go with 30 particles, 250 iterations. And as you can see, the majority of the particles are in fact between the two lines and inside the circle. One more time. And again, you can see clearly that most of the particles actually obey the inequalities that we have. Okay, let's see what happens if we say that, okay, we want the f1 to be greater than 1. So we want to be outside the unit circle and between the two lines. As you can see, we are outside the unit circle and between the two lines. Okay, and again we get -1. It's 1.34 minus 1.18. The sum of the two should be between 0 and 1, and the square of the two should be greater than 1. Okay, so we are outside the circle. This is our random start position, and this is our solution after 250 iterations. Pretty fast, pretty good, and we get a good result. So definitely use particle swarm optimization for any sort of optimization that you have, or any problem that you can in fact turn into an optimization problem, minimization or maximization. Okay, So here I turned a system of inequalities into a equivalent fitness function, and I define it such that minimizing the fitness function is happens if and only if all the inequalities are satisfied, and it gives you a good answer. Okay, now let's say we want to be between two circles, 0 less than f1 and let's say 0.5 less than f1 less than 1, and we cannot do this, we have to break it, f1 greater than f1 less than 1. So now we are in a strip of distance 0.5 and 0.1 from the origin. All right, let's see what happens here. And as you can see, this the majority of the particles are here, and again this is obviously in the circle we are from 0.5, we are between 0.5 and 0.1, and as you can see the sum of the two is between 0 and 1, and then the squares of the two, this gives us probably 0.4, and this gives us 0.4 something, so we are 0.8, we are between 0.5 and 1. So it also works in this case. Okay, so I hope you enjoyed this video, and this is basically one of the interesting things to do with PSO, and thank you very much, and I'll see you in the next video.